In this example, we're going to investigate the usage of a feedback control device in order to try to maintain a constant speed of this van as it moves down the road. So let's first look at the dynamical equations that we have for the van and then put together our feedback control loop and then see how that matches up with the block diagram that's shown here in the picture. So let's begin by looking at forces that are acting on the van. We have a traction force. Let's say that the van is a rear-wheel drive, so we have a traction force here F acting on the back. We're going to model the drag force that's acting on the van as being proportional to the speed. We have weight force here of mg, which is at an angle of theta here with respect to the road. I'm going to put x and y like this. And then, of course, there's some other reaction forces here at the wheel. But if we sum forces in x, the only thing we have to worry about here are the forces of traction, which is F. Drag force acting in the minus x, we have the weight force mg times sine of the angle. And that's, by Newton's second law, that's equal to mass times acceleration, which is v dot. Let's assume that any angle of inclination to the road is small enough that we can replace sine by the angle itself. So with this, we'll take Laplace transform of this. We're looking for transfer functions. Therefore, forced response, we can set initial conditions equal to a 0, and we get Fs minus c times the transformed velocity v minus mg, the transformed road angle here of theta, and then on the right hand side we have m times Laplace transform v dot, that's just s times v. So from this equation, what I'm going to do is bring all my v's together. I get ms plus c times the Laplace transform v, and then on the right hand side I have f minus mg of theta. I want to get the transfer function between Vs and the traction force and the disturbance of the inclination of the road, so I'll write Vs then as being 1 over ms plus c times f minus mg theta, which I left off my g here, so please put that into your equation. So this is going to be our transfer function, which we'll call for the plant, for the car, which is really the transfer function between the traction force and the disturbance due to the change in inclination of the road and the output there of v. So this part here is representing this portion of our block diagram above, where if I let the disturbance d here being mg times a theta, so this is d. So it's the difference here between f, which is going to be the input for this block here, f minus d times this plant transfer function there of gp. Now, what we're going to do is say it makes sense to put a traction force on there, which is proportional to the error that we have between where we want to be and where we actually are. So this is going to be a proportional controller, Kc, times the difference between our desired speed, Vr, and the actual speed there of v. So this is our controller. the interpretation of this is that our traction force is proportional to the error in speed. As that. So, if I put our controller in for the traction force like this, what I end up with is V is equal to GP times KC times the difference between a reference speed and the true speed, here V minus D. We want to reduce this down. Well, first let me say that what this represents here now is our complete block diagram above here. Okay. So then we want to reduce this down to a single input-output equation and bring my GP times our gain KC times V over on the left-hand side. On the right-hand side, I have a KC times GP VR, and I have a GP times D. So therefore, what we have here is V, the output, is GP times KC divided by 1 plus GP KC. That's the transfer function between the speed and our reference speed. So we'll call that GR. And then I have GP divided by 1 plus KC. I'm getting my subscripts mixed up here. I have GPKC like this, and our disturbance there, D. So this is going to be GD. So if I let's do GD first, because we see that GR is proportional to GD. GD, again, that's GP divided by 1 plus GPKC. GP was equal to 1 over MS plus C divided by 1 plus KC divided by MS plus C, as that, and that gets multiplied by KC. I've already got the KC multiplying there. And therefore, when I multiply top and bottom by MS plus C, I get 1 over MS damping drag coefficient C plus our gain there of KC, and then our transfer function between the input speed and the output speed is just KC times GD, as that. So we see with the role here that's played by our gain here of KC is it effectively increases the drag on the car in a way that increase is equal to KC. So let's find out how our control system performs. We're going to do two different tests here. Let's look first at the case of the disturbance equal to 0. In other words, it's a horizontal road. And we'll look at a step input. So the VR is equal to VO over S. So that's a step input. In other words, you turn your speed controller on for the van. You just flipped it on. Your desired speed there is VO. So in this case, with no disturbance, then our output V is equal to KC divided by MS plus C plus KC, as that, times our input here, VO over S. And what I'm going to do is put this first order denominator in a standard form, I'm going to divide through by C plus Kc. And so I get M divided by C plus Kc, S plus 1. And the reason for writing it in this form is that this we know becomes our time constant there of tau. So the two things we want to check out is what ends up being the steady state speed moving along this horizontal road. So the steady state speed VSS from the final value theorem is the limit as S goes to a 0 of S times Vs. So the S here cancels out the S in the denominator, and we end up simply getting Kc divided by C plus Kc times VO. And so the goal here, I think it says, that we want to find the gain Kc such that our steady state is at least within 0.98 of our desired speed there of VO. So VO will cancel out on both sides. And from this, I find out that the gain that I need, Kc, has to be at least as large as 49 times C. So this is the requirement we have on gain in order to reach within 98% of the speed that we desire. The other issue here has to do with the settling time Ts. We know that Ts is roughly equal to 4 tau. So in this case, what we're looking for is that 4 tau is no greater than 4 seconds in time. So this says here that tau, therefore, which is equal to what we see, M divided by C plus Kc, must be less than 1. So therefore, our gain that we need to satisfy that says that the gain has to be at least as large as the difference between M and C. So both of these criteria, given that we know the drag coefficient there is C, we know the mass M of the van, we have to meet both of those conditions in order to meet both criteria of within 98% of the desired speed, and we want to get there within 2% of that within 4 seconds of time. The second question that we might pose is, what if there is a disturbance? In other words, the van in the initial test here was moving down a horizontal road. What if we say now it hits a small incline? So we'll say that theta t is going to be a step change. It's going to be like theta naught h of t, step change. So in terms of Laplace world, then theta s then is equal to this angle here of theta divided by s. So d of s in this case, our disturbance we said was equal to mg times the angle, so that's mg theta naught divided by s. So now we do the final value theorem again and see that VSS, which is the limit S goes to a 0 of S times Vs. Now with both the disturbance and the input speed, what we find out here is that the steady state speed goes as we saw before, Kc divided by C plus Kc, multiplied by the desired speed there of V naught, minus the weight mg divided by C plus Kc, times the angle of inclination there of the road. So again, we talked about this here. What does Kc have to be in order to be within 98% or whatever that we want? But keep in mind that our disturbance here will always take away from that. So the actual speed in going up the incline will be less by a ratio of the weight of the van divided by c plus the gain Kc times whatever angle that we have here for the road. So I think the point of this example is really looking at being able to control the speed of the van. How do we get the block diagram? Because everything else that falls after that is very much along the same line of what we've been doing all along with our analysis and design work. So the idea here was to first come up with the block diagram for our plant with a disturbance. We define a controller. We're saying here it's a proportional control. The traction force to correct for the speed is going to be proportional to the difference in speed, what we want it to be and where it actually is. That's where we get this thing. We use our usual block diagram reduction idea in order to get our input-output equation with a disturbance as this. And again, we look at the performance of it basically in terms of the poles of our transfer function of GR. Well, GR in this case was a first order one, so we didn't have to worry about overshoot. We just really had to worry about what influence does Kc have on the time constant, and that told us a lot about the settling time there of Ts.